Yeah.
Charu, we have two students online. Charu, did you see my email about the plus two this week?
Yes, I did, but I was hoping the last slide.
Okay, so can you communicate with Nigel and Falcon? All right. Okay, let's get started where we left off. We didn't go very far, so I don't really have um recap much for you, but this is fresh in your mind. You have been doing fat analysis this week. So just maybe a quick question, why do we care about fat analysis? Just to get you back into the groove of fat analysis. Why is it important? Or why do we care? You tell me.
Like nutrition labeling and that kind of things.
Nutrition labeling, content claim, or nutrient claims, very good. Like skim milk, low fat milk, and also total fat, total saturated fat. But total fat is what we want for fat. What one more thing, please? Center of identity, very good. One last thing.
It affects the shelf life.
Stability. Higher fat content, you start having potential issues with the acidity over time. Okay, very good. So let's get into it. I guess I was about to tell you a story about goldfish, but let me explain how it works, and then I will proceed with my story. Okay, so it is a continuous, not semi-continuous. So software which you did in the lab is semi-continuous, and one of you answered my question of why is it semi-continuous? Because the solvent evaporates, go into the distillation unit, and then drips onto the sample, and there is a soaking stack. And then it continues, the cycle continues. Here, there is no soaking stack. So what happens is you have your hot plate. I'm going to draw this piece by piece, hot plate. And then you have a distillation unit. Not very straight, but you have inside, you have water running through. You don't usually see it in this apparatus, so it's distillation. And then you remember you all work with symbols, right? Same thing. You want a symbol which you weigh in your sample. And it is poured. That's your symbol. It's always good to have, you use glass wool, right? Put it on top, so you can use glass wool too. And what you see in this picture is you probably only see a beaker, but in between or in the middle of it, you put your symbol in a glass thing that is open from here. It's open to the sample, to the way you put your solvent. So you put your solvent in a beaker here, solvent, but solvent. And then you have your sample in a thimble, and then you have the glass, another glass thing that you put your thimble in it. Thimble doesn't fall into the solvent, it just gets soaked in. And you put that, all of that on that hot plate. Okay, so I do it there. So And there is something that you use to screw the whole thing on, to screw it on to the distill. So the same thing happens. So solvent evaporates because of that hot plate, all closed system, and then goes up into the distillation unit and then drips into the sample. And the cycle continues. There is no soaking step. There is a question in your for your lab report that you probably went through in lab. Did you talk about channeling? What does channeling mean? You remember it, Tyler?
Channeling is when we, or not necessarily, it's there's paths of least resistance where the salt, where the extracting oil to go through, and you kind of mix
You
some
mix it.
pockets. Like that.
Okay, so the channeling, I'll put it in simple term. You're right, but I will put it in simple term. The solvent goes up, distills through the sample, but gets no chance to take out fat. So it goes up and down through the sample without carrying fat. And there's no this allowing soaking to happen. Like in Soxhlet, the solvent goes up, it drips onto the sample, stays in the solvent compartment or the compartment with solvent in it. So it gives it some time to solubilize, then it siphons into the original solvent. Here, there is no siphoning, no soaking, it goes up and down, and it is potentially channeling can happen and underestimation can. Because then you don't have this time to soak and solubilize the fat. It just goes up and down, takes some fat with it, but not always. So that is what is meant by channel. So it's a continuous process. Sometimes you think maybe if I put it longer, it will help. So, but it's not really a good method for low fat samples that it's really hard to get to the fat anyway in a complex matrix. But it works. It for high fat samples, it gets you as close as possible to real results. So some labs have it, so they use it, they don't have Soxhlet, and that's when I was at TA, this is what we use, and this is when I almost caused an explosion. Because if you don't close that, I don't have my pointer today with me. If you don't close that top part, the one that you screw on, if you don't close it very well, you have leaking. And then if solvent leaks onto the hot plate, what happens? It's flammable, especially if you're using ethyl ether instead of petroleum ether. So one time I was teaching and there were students in front of me and I was doing the Soxhlet. I turned around and I noticed it dripping. There was no time to do anything. It just exploded. So my bangs burned, my eyebrows burned. And I turned around, I was so worried about liability and students, like, are you okay? And then everybody's okay. So I got the blast. So yeah. And then I thought, okay, moving on from goldfish, when I came here, I saw Soxhlet. I was like, this is safer. Let me tell you another story. When I came here, the first year that I taught for the analysis, I saw Soxhlet that I never worked with Soxhlet before, but it seemed like it's a safer unit. And I didn't have it under the hood. I had it on the bench. Because I didn't know any better. So what happens in Soxhlet, you already did it in the lab. So you have this condenser, much longer condenser than the one that is used for goldfish. So the solvent evaporates and you have quite a bit of space or length for it to distill. So the solvent doesn't usually even reach the top part of the distiller. It gets distilled in the middle and down. So it appeared safe, but what happens here, like we did in the lab, you put about 300 milliliter of solvent. You also put it on a hot plate so you don't turn it up so high. And then the solvent evaporates, goes up, distills into the thimble. That's the compartment where the solvent gets filled. And then you have this arm, siphoning arm, and then the solvent with the fat siphons down and the cycle continues. Now, it looks safe, but it's not if you have the hot plate on high. So neither I nor the TAs that I had at the time, I'm not gonna blame the TAs, but actually what it is, that we both know about the safety measures for Soxford. So I walked into the lab, we started teaching, and then the hot plate was on high. It was constant. So the solvent was boiling. So it was going up, and then it didn't have time to condense down. It was coming out from the top onto the plate. Okay, I panicked. It's time because I knew the explosion that could happen. I sent all the students outside. I said, get out, don't panic. And they looked at me and they said, Pam, you're the one panicking. Yeah, I know what has happened. And then we let everybody out, turn down the heat, and luckily I didn't get burnt this time. So, but from that on, the Soxit is under the hood for safety measures. No matter how safe it looks, it's not really when you're working with flammable solvents. Okay. That's that. So both goldfish and Soxit method are gravimetric, meaning you take the weight and you either weigh the defatted sample, or if you have a small amount of solvent, you can pre-weigh the flask and evaporate the solvent and then weigh the flask again. So we do that actually in goldfish because the beaker is small and we put much less amount of solvent in it. We actually dry the solvent and weigh the beaker, and the difference in weight is your fat. But in Soxhlet, given that you use 300 milliliter of solvent, you can take that and put it on a rotovap, where you can evaporate under vacuum with a little bit of heat. But that takes a long time, given that it's 300 milliliters. So what you do instead is you take the weight of your thimble with everything in it, and then after we leave it overnight for a little bit to dry out from residual solvent, you weigh it again. And the difference in weight is your fat content. So you did fat content for cheeses on dry basis for Soxhlet. Okay, so this is part of the calculations that you will be doing. So the difference in weight will give you the percent or the amount of fat divided by gram of your dry sample, if it's cheese in this case, times 100 gives you the fat percent on dry basis. So if you calculated fat percent on dry basis and it was 15%, what would it be on wet basis if moisture content is 20%? So next week, we're going to give you the moisture content of all of your samples, or the most accurate moisture content you determine. And you're going to use that for the cheeses to calculate from dry to wet, and also all other samples from wet to dry. So take out a little piece of paper for a +2 and do the math, please.
No, my phone is. Seven.
So this is how you wanna think about it. So in 100 grams of sample that is wet sample, you have 80 grams of salt. The what this is saying is 15 grams, 15% on solid or dry basis. That means 15 grams of fat in 100 grams salt. Okay, so with that in mind, what would be the percent fat on wet basis? Did you do it, Sophie?
Not well. I would rather someone else answer.
Okay, that's all right. That's all right. Anybody got an answer? Percent fat on what basis? So you have percent fat on dry basis. 12%. Yeah. So 12%. Can you tell me how you did that?
So not like how you did that.
Not how I did that. Oh, I'm old. I use old method. You tell me. You're younger, much younger than me.
Birds going around.
What's that? What's that, Red?
Birds going around.
No, actually, I'm giving her a compliment. Okay, guys. Goldfish burns. That's so. What was your equation?
That's how I didn't know equation. It's just that.
It's in your head. Oh, no equation. Okay. Yeah, go ahead, Gray. What?
Mixture times by 1 minus, well, not 100% minus 20%. And then all that times by 150%.
You come up and do it.
Yeah.
Come on, Gray. It's your turn to teach. I'm tired. It's Friday.
We're all tired.
Yeah. Go ahead, Gray. Okay. Okay, it's fine. I have my phone go off every.
This would be, thank you.
Very good. I'm gonna tell them.
Oh, this is the moisture.
This is not the moisture, this is the fat.
Oh, yes, okay, fat. Oops. Fat times by the moisture. But you don't want to times by the moisture, you want to times by the solid amount. So you want to do whatever the moisture is.
Not the moisture, the 100% is all of your sample,
Yeah,
right? Yeah,
yeah.
that's what you meant.
So
Okay,
you want just the solid.
yes, you want the solid, so you take everything, all your sample, 100% minus the 20%. Yeah,
Times by the fat,
yeah,
which then will give you the.
yes. You have questions for Greg? Okay, thank you. Well done. Okay. So that's exactly what he did, but I used my own way of thinking about it. Is like I get the total solids, which is 80 grams. This total fat is 15 and 100 grams of solid. So how much in an 80? So my way of thinking is I have 15 in 100 grams of solid. That's how I always think about it. This is how I learned my math when I was young. How much? So how much do I have in 80 grams? And usually you do this. I don't know if this is a very old way of doing math, right? You're solving for x. So 80 times 15 divided by 100. That's my way, but everybody has their own way of doing math. You can follow Gray's way or my way, whatever brings the same answer, I don't mind. You just show your calculations and go from there. Okay. So moving on to Mojo, which you did already in the lab, and it is also based on solvent extraction, but it is discontinuous, meaning it's a batch process. There is no solvent circulating. So here you weighed your sample. If it was cheese, we dissolved it for you in ammonium hydroxide. So do you remember why ammonium hydroxide was used for cheese sample if you're a cheese group? Mitchell. Well, solubilize the protein. We didn't really break down the protein into peptides. We just helped because in cheese, the proteins are formed in a gel-like matrix we call the curd. So if we don't break down that matrix, the fat is entrapped, we can't get it out. So the ammonium hydroxide is treated or is used to solubilize the protein. But for samples that were high in carbohydrates, so your Cheerios, your baby cereal, and you have almond, which is a combination of high in a little bit of carbohydrate, sugars, and fat and proteins, we use HCl to break down everything to release the fat. In this method, we don't want moisture. We don't have to dry your sample. And one of you answered last time, why don't we have to dry the sample if it's high in moisture like cheese? What was the difference here between this and Soxlet? Somebody said, shake, shake, shake. Who answered that question? Somebody answered this. You did. So, yeah. Okay, so here there is this shaking, and then you change, you put 3 times fresh solvent. You shake, 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 dispense into your pre-weighed pan, you put fresh solvent and shake, shake, shake again. So that's why you don't necessarily need to dry your sample because you force the solvent to reach the fat, especially if the protein matrix in cheese has been solubilized and if everything was hydrolyzed using the acid. So that would make it, with shaking, easy for the fat to be solubilized in your solvent, and we do that 3 times. You collect the pan, you dry the solvent, and then you weigh the pan again, and you get the total fat weight. by the difference, removing the weight of the pan. Okay, so why did you use ethanol? Do you remember? Adding ethanol during the digestion. Why was ethanol added? This is a question in your lab report. You're going to tell us why you added ethanol. So it's an alcohol. We added it. Anybody remembers? Yes. To get it what? To stick, to clump, to hold on to. If you don't have alcohol, when you add the HCl, for example, the protein might clump together when you add the HCl, and you won't get that fat out. Your fat will be entrapped in clumps. So things might stick to the side. So the alcohol loosen things up and keep them dispersed, so that when you're extracting with ethanol, with pet ether and diethyl ether, nothing really is entrapped with the matrix. Okay, so that's the role of the alcohol, dispersing everything. And we use combination of ethyl ether and petroleum ether. Do you remember why sometimes combination is preferred? Yeah, to encourage different lipids with different polarities and solubility to be extracted. If I use only pet ether, mostly triglycerides will be extracted. If you have any relatively polar sections or fractions, they won't be efficiently extracted. If I only use ethyl ether, some of the triglycerides might not be efficiently extracted because of their very hydrophobic nature. So a combination of both. In this case, it's feasible because you only add 25 milliliters of each. In Soxhlet, remember, you add 300 milliliters. So it's going to be so expensive if I'm going to use ethyl ether because it's an expensive solvent. So in Soxhlet, you use petroleum ether. Okay, so another way to extract fat based also on extracting based on the hydrophobicity of the lipid component. So here we use supercritical fluid extraction. So CO2 under high pressure and temperature becomes liquid. So it goes into the cell of where your sample is as liquid under pressure. And then after it extracts the fat, that liquid phase is pushed into a collection vessel or vial. Once it goes, the pressure gets reduced to atmospheric pressure, CO2 obviously becomes gaseous, and what's left is your fat, and you weigh that and you get the fat. Sometimes you add methanol with CO2 to help extract more polar lipid because methanol is a relatively polar organic solvent. This type of extraction works well with GC analysis, depending on the components or the fractions we are extracting. So it can be linked to GC. Okay. The other one is accelerated solvent extraction. Here we also use a salt. We use a solvent in this case. We don't use CO2, but also under pressure and under pressure, the boiling point is higher. So you enhance the efficiency of extraction at higher temperature. And the same thing, you would collect that fraction, and when you reduce the pressure, you can evaporate the solvent more easily and collect the fat. You can run it in static mode where you are just allowing it to soak and extract, or in dynamic where that valve is open and you continuously put solvent and extract. Now, of course, we can have better efficiency when it is open, not static, or continuous, not static. But the issue with that is you use a lot of solvent. So it might be a little bit more expensive. Okay, the last, well, not very last, but among the last thing is extraction of fat from dairy is commonly used by using Babcock method. You know, in Wisconsin, there is a Babcock building. You know that? It's the dairy building in Wisconsin. So Babcock is a guy, a professor back in Wisconsin. So oftentimes the methods are named after the person that developed them. Okay, piece of history. So you have three different shapes of Babcock flask. One A is used for milk, B is used for cream, C is for cheese. And you can see there is this fork that you remove to put in the sample because cheese you can't just pour down. So you weigh your sample. Well, actually, it's volume based, especially for milk. You put a known amount of milk with the same volume of concentrated sulfuric acid. I believe it's 17.6 or 17.8 milliliter. You don't have to remember that, but it is same amount of volume for milk and concentrated sulfuric acid. As soon as you add the sulfuric acid, it's going to start to digest your sample in an exothermic reaction, going to generate heat, and the fat is going to be in a liquid form and separate based on density and goes up into the neck, and you measure the volume of fat. So it is a volumetric, not gravimetric. You're measuring the volume of fat. And by knowing the density of fat and the density of milk, you can determine the concentration of fat weight by weight. So digesting the sample with concentrated acid, it's an exothermic reaction. I'm just repeating so that you capture everything. That generates heat. The heat allows the fat to be in liquid form. And because of difference in density, it's going to go up to the neck of the tube and you can measure the volume. And the sulfuric acid breaks down everything, digests everything. The sugar, the carbohydrate, well, sugars in this case, the proteins, the triglycerides, and then what you get is the fatty component that goes up to that neck. Gerber method, it's a French guy. So Gerber, it's the same method. The only difference is the shape of the flask is different, and you use alcohol to prevent the charring of sugar, so you have better reading, you don't have that blackening. That's it. The principle is the same. There is a centrifugation step I forgot to mention here. After you digest and then separation happens, the centrifugation enhances the separation so that the fat is for sure in the top graduated area. So same piece of paper, let's do some math. Here you're given that the milk fat density is 0.9 and the milk density is 1.032. So now you have the density of milk and the density of milk fat. And you determine the volume of fat percent is 3.55, which means 3.5 milliliter in 100 milliliter of milk. So 3.55 milliliter of fat in 100 milliliter of milk. What would be the percentage on what weight basis? Weight. So that means weight by weight. Okay, so think about it for a second. You have an answer, let me know. So what is the first step that you need to do? It gave you density. What would that give you? Go ahead, Mitchell.
Just the weights.
Yeah, so you use the density to get the weight of the fat, and you use the density to get the weight of milk. So 3.55, right? So 3.55 means you have 3.55 milliliter of fat in 100 milliliter of milk. That's what it's telling you. So what is density? Density equals mass over volume. So you have the density of fat and you have the volume of fat, so you can calculate mass. So mass equals density and volume. So what's the density of fat? 0.9 grams per milliliter, correct? Is that what it said?
Yeah.
All right. And then the volume is 3.55 milliliter. So milliliter, unit cancel. Always remember to put your unit. And then what would be the mass in this case? 0.9 times 3.55.
It's 195.
3.195 grams, right? Okay. That is the mass of fat, the weight of fat. So the percentage I've got is that 3.55 milliliter is on 100 milliliter of milk. Now I want to get the mass or weight of 100 milliliter of milk. So the mass equal, again, density times volume of milk this time. Here is of fat. So what is the density of milk? 1.8 grams per milliliter. And the volume is my 100 milliliter. This is 100 milliliters. So unit cancel. And that means 103.2 grams. So now I have 3195 in 103.2 grams times 100 will give me a percentage. So 3.195 in 103.2 grams times 100 would give me, what's the value? 3195 divided by 103.2. 3.1%? 3.1. 3.1%. All right. Do you want me to repeat anything? Let me know. Is there anything where you got lost? Okay. Okay to repeat? All right. Okay, so instrumental methods. So infrared, we talked about IR. The only thing in IR for fat analysis, depending on the sample, you can use mid IR or near IR, but you just need to calibrate. You would calibrate your IR instrument using either Mojo results or Soxit results. And then you can measure your fat content online as quality assessment. The first layer method is really determining your fat content based on density. So you would measure, well, you extract the fat in a solvent, and you have your solvent that you use and the fat with the solvent. You measure the density and you use a conversion chart to get the percentage of fat. Last one is NMR. It is an accurate method for determining fat content. If you have NMR in your lab, and if you have a trained technician, that's a good method of determining fat content. So that's it for fat analysis. I have 7 minutes. I'll introduce protein, which you will do next week. Bye. Where is this? Why does it do this to me? I'm not seeing the. I'm not seeing it. Ah, there it is. Why is it doing that? I have no idea. Okay. Let's do a couple of just knowledge check of the amino acids that you know. Which of these statements is correct? Of what you know about amino acids and protein. Well, amino acids in this case. Sure. A and C. A and C. We have only 3 amino acids that absorb light, UV light specifically. So they are tyrosine, tryptophan, phenylalanine. All other amino acids don't. Even proline, that looks like it's a cyclic amine, but it doesn't have the actual ring, that benzene ring that allows it to absorb light. So really, only tyrosine, phenylalanine, and tryptophan absorb in this region, and the 2 that absorb the most, or the highest molar extinction, is phenylalanine and tryptophan. Sorry, tyrosine. Tryptophan is the least absorbing, but it still absorbs light. So this characteristic allow us to measure protein using protein in solution using spectrophotometer under UV light. So all proteins, regardless of their source, they have a certain amount of these amino acids. There is no protein, as far as I know, on Earth, let me just say on Earth, because I don't know what's outside of Earth, that doesn't contain a certain amount of these 3 amino acids. So this means that if you have a protein in solution, especially a clear solution, I'll talk about that later, you don't want any interferences. A clear solution of protein, you can measure the UV absorption of that, and using a standard curve, you can convert the absorption to concentration. Now, if you have peptides, can you still use UV absorption for peptides? What is a peptide? Protein broken down by enzymes or any other chemical reaction into smaller sequences, peptides. Do all peptides absorb light? Think about it. No, why, Tyler?
They're short of things, so they don't all have.
They don't, yeah, they don't all have potentially. This depends where you cut. Dipeptide, tripeptide, or even bigger peptides might not necessarily in their sequence have any of those. But from what we know about a peptide bond, what is a peptide bond? Scratch your head, Sumili. Yes. So Sumili says A and C. Do you agree or do you have a different answer? Do you remember what is peptide bond? Do you agree, Graham? So Graham says A and B. Anybody else? Sierra? Just A. It's just A. What is then the peptide bond? It's a covalent bond, sure, but it is between a carboxyl group of one amino acid and amine group of another amino acid. So not two carboxyl groups and not two amine groups. Okay, so why do I care? I'm just trying to see how much you remember from your food chemistry class, but also peptides absorb UV light between 216, 214, depending on the method that you use in your lab, to 222 and around that. So if you have peptides in your sample and you still want to use UV light, you could, but then you want to use the wavelength at which your peptide bond absorbs light. So which is anywhere between 214 to 222, somewhere in that region. Okay. Let's do this and then I'll let you go. Why is it important to analyze protein content? Why do we care about protein? Because Pam cares about protein. That's the correct answer, obviously. No, go ahead. Nutrition labeling, of course, yes. We need the quantity because on your label, you have percent protein. What else? Sometimes you need to make a claim, right? High in protein, a good source of protein, so you want to know if you can make that claim. What else? What's important? Yes, please. Quality, yes, quality. That's very good. Sometimes in my world, I deal with a lot of protein ingredients. The nomenclature of these protein ingredients depend on their protein content. So is it a protein concentrate? Is it a protein isolate? So I need to know the protein content so I can claim it's a concentrate, it's an isolate. So it has to do with my sample characterization, my quality of the sample. But there's another, what if proteins are enzymes? When I determine protease activity, or even lipase activity, or lipoxygenase activity, usually it's units per gram of protein. So I need to know the amount of protein, and then I report my unit per gram of protein. This is a college board question. For all of you, I want to do it. Define the enzyme unit of activity. It's not, this is half of the definition. I'm not going to tell you the full definition now, but you need the grams of protein in order to report activity of the enzyme. Another important thing in our world, or my world and my students' world, is we determine protein functionality, like emulsification or gelation. We need to know the amount of protein because we report it per gram of protein. So these are the kind of the importance for that. What methods do you know of for protein? What have you heard of? Did you hear of any methods we used, Okay.
So I have one of the methods is like nitrogen content.
So we have two methods that we use for determining protein based on nitrogen content. And those two methods you're going to be using in the lab next week. These are Kelda and Dumas. So both of them will give you the total nitrogen, and you convert that to protein content based on a general percentage of nitrogen in your protein source. Infrared, we can calibrate it using Keldar or Dumas. These two methods are official methods of analysis. Keldar and Dumas are official method of analysis. I'll let you go. Research method, your protein needs to be in pure form, liquid form, no cloudiness. The first three are based on reducing. Bradford is interaction with a dye, and this based on using. Okay, I'll let you guys go. Have a great weekend. Yes, Chuck? About what? College Bowl. Yes. If you're competitive, if you like trivia, we are recruiting for College Bowl team. It's super fun. We have an event on November 20th. Come watch your colleagues play and see if you like this one. Right? November 20th, what time? Do you remember, Kendall? At 5 p.m. Come watch us play. We'll say it again until it's the 20th.
Yeah.
Okay. Oh, Sharu, Rob was answering questions. Did you see?
Yeah, I saw the chat, like,
So he had 7 answers. You captured all of them?
not all, but I saw the Oh. I'll just tell you.
I did a bet. You get close to 9.
Oh, Jordan,
Since you did it.
Charu, there's Jordan answer too,
Okay.
twice. Hi, just a sec. Did I start recording?